Hello and welcome to this course on chemical process modeling and simulation. My name is Murali Rangarajan. I am a professor of chemical engineering and material science at Amrita Vishwa Vidyapeetham, Coimbatore. This is an introductory course on modeling and simulation of chemical processes. Well, modeling and simulation both, whether we realize it or not, play a very critical role in the way we engage with various activities of our life. They play a critical role in not just chemical engineering or engineering in general, but also in a variety of disciplines. Throughout this course, at least in the introductory section of this course, we will encounter a number of examples where we will see how the principles of modeling and simulation give us critical insights and enable us to use those insights to develop strategies, solutions, approaches to handling or solving various problems, not merely in chemical engineering, but in a variety of disciplines, including daily life. Now, of course, this course is an introductory course in the modeling and simulation of chemical processes, and therefore this course will largely be delivered centered from a chemical engineering perspective. And therefore, to get started, get going, we have to understand the kind of problems that chemical engineers face in their profession. And so we do this in this introductory lecture with a case study. We will, using a very simple example, pose a variety of questions, each of which sort of will lead into the kind of problems that chemical engineers face. And then we will also in this lecture get some idea, very preliminary idea, of how the principles of modeling and maybe some simple simulations, which may be just hand calculations or even mental calculations, right? Not necessarily computer simulations too, but not necessarily them alone, right? How this modeling and simulation can be utilized, to solve these chemical engineering problems. So this is the sort of a motivation and overarching introduction using a case study. That's what we are going to do in this introductory lecture. So without much, we will get started. A case study, and here is a very simple example. This is a very simplistic presentation of what would be a chemical industry. And we start with one unit in a chemical industry. We start with a mixer. Consider a mixer which mixes two streams into one. Stream 1 is equimolar or 50 mole percent each of benzene and propylene coming into this mixer at a temperature of 220 degrees Celsius and a pressure of 2 atmospheres. Stream 2, on the other hand, contains 45 mole percent each of benzene and propylene, and the rest of it, which is 10 mole percent, cumene or isopropyl benzene. And this stream enters the mixer at 120 degrees Celsius and 1.8 atmosphere. Now, a typical mixer can be imagined as some sort of a tank. You get these streams come in, and then you have some sort of an agitator, or and you sort of mix these streams together and you draw an outlet. But with gaseous streams such as these, a simple Y junction should do the job. So F1, which and of course this is the variable that I've just given for the flow rate of that particular stream. I'm calling this stream, stream 1, as fresh feed, because of course the output is going to go into something else, and we're going to look at the entire set of sequence of processes. So with that in mind, this is called the fresh feed, and F2 I'm going to call as a recycle stream, right? And F is the mixed stream. Now, given these compositions, if you know the flow rates, will you be able to tell me what would be F? What would be the outlet flow rate of the mixed stream? Will you be able to calculate and determine what would be the compositions of benzene, propylene, and cumene in the mixed stream? Will you be able to calculate and determine what would be the temperature and pressure of the outlet mixed stream? These are the kind of typical questions you've studied in material and energy balances in the sort of the first introductory chemical engineering courses. So these are standard questions actually. Given the input concentrations and flow rates, calculate the output concentration and flow rates. What would be the approach? The approach would be to write conservation equation of the overall mass conservation or of the individual species conservation, and so that will give you the output flow rate and the output concentrations, right? Now, given the input temperatures and the specific heats and the heat of reaction, assuming that there is some amount of reaction between benzene and propylene to form cumene, even in the mixer itself, right? So now, can you calculate the output temperature? What would be the approach? You would write the energy conservation equation and get the output, calculate the output temperature. Now the third one, given the pressures of the inlet streams, can you calculate the outlet pressure? Of course, you also have to know the flow rates, but knowing the flow rates and the pressures of the inlet streams, can you calculate the outlet pressure as well as the pressure in the mixer in the region of the Y junction? And what would be the approach? You would have probably written an equation for the conservation of mechanical energy, and using this equation you would have obtained this outlet pressure. And as I said, these are kind of problems you would have solved in the introductory mass and energy balances courses. Now let's move a little bit further. If the outlet temperature cannot be lesser than a certain value, then how does one design or operate the mixer? Now, I hope you can see that I am placing a constraint, an operational constraint on the outlet temperature of the mixer. Such constraints arise very commonly in chemical engineering problems. One common example why you would see such constraints, especially of temperatures, is because you want to maintain a certain temperature or at least a certain minimum temperature in a subsequent unit. For example, it could be in a reactor. Now, how would you do this? What would be the approach? This is a control problem, process control problem. Here you are trying to say that I am going to maintain my temperature at least at a certain value. That's the constraint that is given. It could be, I don't know, 200 degrees Celsius or some number, definitely some number above probably 120 degrees Celsius, which is the temperature of the recycled stream. Now, you have to ask yourself, whenever there is a control problem, what is the manipulated variable? You know the control variable. The control variable is the outlet temperature. Now, what variable are you going to manipulate in the mixing process to achieve this desired outlet temperature, right? Now, in a Y junction, really there is not much of a say in terms of a pressure to expand a gas and then cool it or whatever it is. So typically what you would then do is your fresh feed stream is likely to be the manipulated variable. This basically means you're going to change that inlet temperature from 220 degrees Celsius to whatever it has to be so that the outlet temperature, is not lesser than a certain desired value. Similarly, if the outlet concentration of cumene cannot be greater than or less than certain limits, how does one design or operate the mixer? Of course, this issue could arise in a practical situation if a subsequent process of formation of cumene, as you can guess, there is likely to be a reactor downstream, right? If that reaction itself is highly reversible, you don't want a whole lot of product at the entrance, so you may want to control the outlet concentration of cumene in the mixer. Or this actually may more frequently arise if you had some sort of inerts. You don't want to keep building up the concentration of inerts inside a reactor, especially when you recycle a stream. You would have been introduced to this, I assume, in your material balance, energy balance courses. And so this again is a constraint on the concentration of some specific species. And this is what would be the approach. This is also, again, since it is a constraint, you need to meet this constraint. So you have to come up with a control strategy for that particular variable, which is the controlled variable, which is in this case would be the outlet concentration of cumene. So once again, what would be the manipulated variable? There are, either you have to change the composition of the recycled stream, or you have to change the composition of the fresh stream. The recycled stream is coming from the downstream processes, downstream units, and so there is no, there may be other issues if I have to tweak that. So probably, one logical manipulated variable would be the fresh feed itself. Now, if the outlet pressure cannot decrease below a certain value, how does one operate the mixer? Now, this is again another constraint on the pressure, one of the operating process variables. How do you design again? What is the manipulated variable? So, in a Y junction, really, how do you come up with a design, right? So one way to look at this to change the outlet pressure would be to change the angle of the Y, isn't it? So that is one way in which you could change the outlet pressure. So there are various. This could therefore be. I put a Y junction design and a question mark because basically this could mean sort of a design variable constraint, meaning in your Y junction your angle should not be less than this or greater than this, and so on and so forth. So that is one way to look at this. Once again, of course, you can change the outlet pressure by increasing or changing the pressure of the fresh feed stream. So these are some of typical chemical engineering problems that we chemical engineers face in our profession. Now let's go further and look at the rest of the units in this cumene synthesis problem, right? So you have a mixer, and in this case I just showed a simple Y junction, and then you have a reactor, and in your mixer your pure feed is benzene and propylene, and then the recycled stream has 10% cumene, and then now you have a reactor where this reaction takes place, and data is given to you, information is given to you that this reaction is exothermic, and some conversion is given. I mean, either or you design the reactor for that conversion, a single pass conversion or an overall conversion. And then you take this gas and you want to separate benzene, propylene from cumene, and so you cool it down partially to some temperature, and then you have a separator where you get your product as a certain purity of cumene, and 150 degrees Celsius, 1.9 atmosphere pressure, and then the the gaseous phase is essentially either condensed or, no, in this case not condensed, and then it is recycled back into the mixer. And to solve material energy balance problems, you will need to have data like this. There may be many other data that you may need. For example, you may need the rate constants involved in this reaction. You will have a variety of data that will be available. I've just given this as one example data for calculating the specific heats of the benzene, propylene, and cumene species. You will have various data. You're familiar, I'm assuming, in using these data and solving such problems as were posed earlier. Taking this further, I want to ask more challenging questions. Suppose the reactor downstream has had a problem and it has resulted in a poorer conversion than one would expect. What happens to the outlet temperature from the reactor? What happens to the concentrations of benzene, propylene, and cumene coming out of the reactor? And therefore, the outlet temperature and concentrations going into the distillation column or separation column. What happens to the product, cumene temperature and concentration? What happens to the temperature and concentration that the initial set concentration of 45 mole percent of benzene, 45 mole percent of propylene, 10 mole percent of cumene, 120 degrees Celsius, 1.8 atmosphere pressure of that recycled stream? What happens? Okay, so if there is a change to this outlet temperature and concentration, now you are mixing it with your fresh stream, what happens to the inlet to the reactor? Now this is, you see, a feedback loop. So there was one problem with the reactor downstream. The conversion dropped from 90% to say 80%. Now what will this mean? This means that you will have more unreacted benzene and propylene coming out, going into the separation unit. Now this means there will be more of those benzene and propylene staying in the product stream. And that means less of cumene probably going into the recycled stream. Now, since this reaction is an exothermic reaction, now since you did not have sufficient reaction, that means the energy released in the reactor would be lesser, and therefore that means your outlet temperature would not be as high as you would have initially expected, which means the cooler would have cooled, unless you did something at the cooler, it would have cooled the product mixture to a temperature lower than 130 degrees Celsius, which basically means, the temperature of your recycled stream is dropping below 120 degrees Celsius, right? So your feed into the reactor basically after the recycling is going to be at a lower temperature than usual, which means for an exothermic reaction, your conversion will drop further. I hope you are able to follow this sequence. This whole sequence tells you something. This means that such a problem when it is fed back, does not tend to fix this problem, but it tends to make the problem worse. And this means unless you control the whole process accordingly, at various stages, somewhere to fix this poorer conversion, you are going to see a spiraling off of the situation where the reactor would be going away and away and away from the desired state of operation, and the reactor will slowly get into a stage where the conversion is practically not happening. There is simply not enough of reaction happening to produce cumene. So this feedback loop is a destabilizing loop, right? So what would be the control strategy for such a system? What would be the manipulated variable? Where would you control this if it is in the reactor? Where would you control this if it is in the cooler? Where would you control this if it is in the mixer? And what would you do in the separation process? Let's assume that it is a distillation process. What would you do? What sort of strategy would you adopt? Again, this is an analysis problem where you are looking at control strategies to address a scenario. I've posed a what if this happens kind of a scenario, right? And you are trying to see if you can build in these kind of control strategies to prevent such scenarios, undesirable scenarios, from taking place. Another what if scenario. Suppose the recycle stream valve is jammed and is in a fully open mode. What happens? I mean, surely you're not going to just take the top product from the distillation column and put it all into the mixer. You would want some sort of a control in case you are producing something that is not desirable, and you will always have a valve which will allow you to regulate the flow rate of that recycle stream valve. So the recycle stream flow rate can be controlled. And suppose that is jammed and you want to set it at say 90% opening, but it is jammed and it is in fully open mode. Now what happens? You probably send the same stream at a faster rate or at a slightly higher pressure. So what happens? What happens to the outlet temperature and concentration? And I'm sticking to these two because these two, I'm sticking to sort of this question at the mixer outlet. So even though there are these multiple units, we started out looking at what would be the outlet temperature, outlet concentration. I could have added pressure as well. So temperature, pressure, concentration at the mixer outlet after these two streams are mixed. Again, what would be the control strategy to maintain this outlet temperature, outlet pressure, and outlet concentration at the desired values? So in all of these things, these kind of problems, to obtain implementable solutions, what have you done in your chemical engineering courses is that you have always tried to describe this system rather than such a verbose manner that I have described so far. Rather than that, you've tried to come up with you've been exposed to, taught to describe this system in a very crisp, very accurate, mathematical manner. Reproducibly precise mathematical manner. And that is why in chemical engineering, whenever you've looked at all these, starting from mass and energy balance to the various unit operations such as a mixer, which is in this Y junction would be a fluid mechanics problem, to some sort of a heat transfer where you have a cooler, to some sort of a reactor, to some sort of a separator mass transfer operation, in all of these kind of courses, you've always written formulas after formulas after formulas expressing what happens in a chemical engineering unit, right, by way of mathematical equations. You describe the unit in a mathematical equation. You describe the process that is taking place in the unit in a mathematical description. And you use this mathematical equations to obtain various solutions that you implement. So the solution strategy is also obtained in a mathematical fashion. The mathematical solution then translates to some sort of a practical implementable solution. So this is how you've been trained all through in your chemical engineering courses, and this very much is modeling and simulation. Of course, we'll formally define all of these things in subsequent lectures, but I want to sort of I hope that you are able to appreciate that all this time, even though this may be a first lecture in modeling and simulation that you may listen to in this particular course, at least you have been doing modeling and simulation all through your chemical engineering curriculum. Now let's take this further. I want to sort of take this even further. Suppose you have to build an actual plant to execute this process depicted in the flow sheet. I mean, you saw those 4 units in the simplest flow sheet. An actual chemical industry is far more complex, but fine. So how do you develop a layout of the plant? You will probably need some sort of thought process in terms of which equipment do I keep close to each other. There is a linear layout where you have the mixer, there is Y junction, and then a reactor, which is probably some tank or some tubes, basically if it is a plug flow reactor, and then a cooler, which is some sort of a heat exchanger, and then there is a distillation column, and then you place one right after the other, and then you take the top product and then pipe it all the way to the left end, which is your Y junction. Or you could lay it out in a circular fashion, right? So that the distillation column and the Y junction are close to each other. That could be a layout. So how does one develop a layout? What are the issues to be considered in developing the layout? In addition to what I was just talking about, where are you going to get your benzene from? Propylene from? Where are you going to put your cumene, the product, at? Where is your power? Okay, are you just drawing power from the grid, or are you generating some sort of a power in your plant itself? What about steam? You have a heater, cooler. I didn't show all the units that would be there. You could need steam. You could need cooling water. So you may have to have some steam generators. You may have to have some chillers. Where would you put them? And you may need air if you have some sort of a compression in pneumatic processes or whatever. You may need air as well. So the layout itself is another chemical engineering problem, and a chemical engineer would face in her or his profession. Now let's take this one more step further. Suppose you are a process engineer in a company that makes cumene, this company that makes cumene by this process, this 4-step process that we saw, and the CEO calls you and says, I want you to analyze the possibility of replacing this reactor and this separator by a catalytic distillation setup. So you have in one shot, there is no mixing, there is no reaction, there is no separation as individual units. You have one single unit, you collapse all of this into some sort of an intensified catalytic distillation setup. How will you perform this analysis? How much time will you take for this analysis? I assume that, once you come up with some strategy, you will have to test it out if it works or not, and therefore you will have to design and fabricate, at least in the lab scale and maybe then in the pilot scale, catalytic distillation setup, and then you will have to probably run all of these experiments with various feed conditions for, you give benzene and propylene, those are the feed compounds, and then you give them feed them at certain temperature, pressure, flow rate, compositions and then run this and then get all the results and various operating conditions. You optimize what should be the preferred condition where you will maximize the formation of cumene, and you will get as pure a cumene as possible, and then the unreacted benzene cumene are recycled back from, say, I'm just speculating here, from the top of the column, bottom of the column, or something like that, or vice versa. Right, so how much time will you take for this? So you have to design, fabricate, and then run experiments. How many such experiments can you run? Is it possible to look at all possible scenarios, of operation, to determine how best to operate this catalytic distillation setup? Now, is it possible to experimentally study the various safety scenarios? What if there is a temperature runoff? What if there is a pressure runoff? I mean, meaning, so the pressure builds in the system for whatever reason. You're not able to draw a product, and then the whole thing just gets jammed, and you are accumulating more and more. Pressure builds up, right? So, what if you want to study such safety scenarios? You really cannot afford to do those kind of experiments, at least not to the level of catastrophe, right? So you need to have ways in which you not only will you optimize the time that you take for this sort of analysis, and you also have to consider how much cost will it take to sort of give that result, in terms of, hey, here is a catalytic distillation setup, go set it up. You collapse this whole 4-step industry into one unit, right? How much will it cost for you to come to that? Can you predict the various scenarios, as I asked, of how the traditional versus the intensified processes compare for various production rates? There may be a demand for cumene to a certain extent, and then there may be a limitation in terms of how much benzene and propylene you may procure. So, and can you predict for various scenarios how does the traditional process compare with the intensified process? So there may be so many more problems that you may have to tackle as a chemical engineer, than what could be solvable by using experiments alone. And therefore, this also is a very crucial place, a crucial sort of contribution, where you can use the tools of chemical process modeling and the simulation, and on a computer run these various scenarios and look at the various safety issues. What if there is these scenarios, right? And you run these processes so fast that virtually no cost, and so you can come up with a design and use experiments judiciously for validation of whatever simulations you have done, of the models that you've developed, and the simulation of the models that you've carried out. Use experiments judiciously to validate them. And then you say, hey, here is something that works. And you can do that at much lesser time and much lesser cost. And therefore, as you can see, based on this rather longish introduction and case study, there are a variety of problems that a chemical engineer faces and solves on a regular basis. And computational modeling plus simulation approaches, all right, play a significant, a very crucial role, in addition to experimental understanding, in solving these chemical engineering problems. And therefore, here is a list. It's not a very rigorously complete list, but a reasonably complete list. A design problem where you have a certain requirement in terms of a certain type of output you have to produce, and then your raw materials are given. You tell me what the process should be, you tell me what should be the operating conditions, you tell me what type of unit or units, various units should there be, design this mixer, design this reactor, design this heat exchanger, design this distillation column, and so on and so forth. So there are all these unit designs and process designs, which we will see. All of these we will formally define all of these problems, right? So this is one type of chemical engineering problem. Rating is another type of chemical engineering problem. You've been given a set of units specified clearly, and the processes are also given specified clearly. Here is your input. You tell me what the output is going to be. You know, for example, you rate a bulb to be, say, 10 watt or whatever it is. So for this particular voltage, for this particular frequency of the alternating AC supply, AC current that you have, you plug this bulb, you fit that bulb into this power supply, and then the power that it consumes is these many watts. So it is basically a performance characterization, right? So this is a sort of performance specifications that you will get for any product. That is your rating problem. And analysis problem, a variety of analysis problems starting from control to various what if scenarios that we considered. Flow sheeting, and therefore you have to have a series of such units and processes, so which leads to some sort of a development of a flow sheet, analysis of a flow sheet, design of a flow sheet, rating of a flow sheet, and so on. Layout is one thing that we talked about. Commissioning, of course, we didn't talk about this, but if you have developed a layout, you've developed the design, and you go and fabricate actually, and then commission, and then various troubleshooting problems. We considered one intensification problem, quality. Once you're operating, are you always making cumene at the same quality is something that you have to look at, and then handle the production as a whole. And then, of course, you have to address the various environmental issues that arise from a chemical engineering process, from the conception all the way to the regular operation and maintenance and so on and so forth. Various environmental issues may arise which will need to be addressed. And of course, there are legal issues, intellectual property, and so on and so forth. And there is management of this whole industry. So there are so many problems that chemical engineers tackle on a regular basis, and in solving these problems, a mathematical approach followed by computations, simple computations by hand calculator, or more complex computations on a computer, right, to all the way to some large supercomputers, high performance computing facilities. You could go end to end in solving these mathematical models that you develop, right? So this modeling and simulation play a very crucial role in chemical engineers solving various problems such as these that are encountered in their profession, right? So I hope with this case study and this introduction, you've been able to gain some appreciation of why and how modeling and simulation of chemical processes play a major role in chemical engineering profession. So over the next set of lectures, we will first gain an introduction to what a modeling is, what mathematical modeling is. And then we will try and understand what is the general approach, what is the general sort of recipe for modeling. And then we will move into chemical process modeling. We will define various terms, pieces needed to be put in place before we can start this whole modeling exercise. And then towards the end of the course, we will introduce you to some simulation techniques. I want to just make this small caveat before closing this lecture. What we will not be discussing in this course is the various numerical computational techniques that are needed for carrying out the simulation. So for example, this is not a course where you will see anything significant major about computational fluid dynamics, for example. So yes. there will be some opportunity to sort of give a brief introduction to what sort of CFD tools are used, along with a various variety of other tools. But this course will not be focusing a lot on the mathematical aspects of solving various models, though some simulation techniques will be introduced as part of this course. So with this, I thank you for coming all the way to the end of this lecture. And if there are any questions, I welcome you to please post them in the channel, and I'll do my best to answer them. Thank you once again. Looking forward to interacting with you in the upcoming lectures as well. Thank you very much. Have a nice day.